Alrighty, ladies and gentlemen, boys and girls, welcome to another thrilling episode of Mr. Smith Talks About Calculus. In today's episode, we will be doing some applications of the absolute extremum that we were introduced to in section 3.1. You'll note that I am still arrayed in Dodgers garb, it being the 21st day of October, 2020, tonight being the second game of the 2020 World Series. We were victorious last night. Clayton Kershaw threw a vintage Clayton Kershaw game, came home victorious. I'm wearing Chase Utley's player's jersey from a few years back. If you're not familiar with Chase Utley, he's a UCLA grad, which is already a good thing. Played for the Phillies for a lot of years, finished out his career with the Dodgers. One of his claims is that he broke a man's leg with his face sliding into second base, and henceforth the rules about sliding into second base were changed because of that incident. So there's a piece of trivia about Chase Utley. And his nickname was the Silver Fox because he was an older dude for a baseball player in his late 30s, had some gray coming in. Well, it's easy on the eyes, we're so told. He was the Silver Fox. Today I pay tribute to the Silver Fox. Anyway, 3.2 is what we're talking about today. And it's just like word problems, which is every math student's favorite thing, is word problems. So I'm sure this will go super smooth and not have any issues. So here we go. We are sharing screen. Content from second camera. Here we go. Look at that. I already wrote out. 3.2, application involving absolute extremum. Technically, it includes on a closed interval, but I didn't think there was room there, so I didn't write it. And we're just going to jump right in. Actually, no, I'm going to talk for a little bit because that's what I do. One of the applications of calculus that is used a lot is the derivative allows you to optimize certain functions. And when I say optimize, I mean when you have a quantity that can have a max value or a minimum value, this idea of the derivative giving you those locations where those maximums or minimums occur can be useful for people making decisions about how to do certain things in a way that either maximizes that quantity or minimizes that quantity. And we'll see some examples of that today. And these are a little bit contrived in terms of being able to display what we're doing. But this is also very real in terms of this is how, or one of the many ways that calculus is used in the real world is looking at situations and figuring out there's a lot of moving parts. How do we zone in and key in on what we need to know to make a good decision, whether that's maximizing the volume of a box or minimizing the distance between an oil derrick and the shore. All of these things are real uses of calculus in business and life. So this is kind of fun. It's like, oh, when are we going to use this? Well, could use it to figure out for a box manufacturer how to maximize the volume of a box with a certain piece of cardboard. And since I said cardboard, we're going to jump right in and look at the cardboard freaking box. This is example one. No, not even an example. It's an illustration. It's a hell of an illustration, though. So we're going to see the illustration one. And my notes from last year literally have titled this the cardboard freaking box, so that's what we're going to do just for the sake of posterity. The cardboard freaking box. I don't know why I was so frustrated with this box last year, but apparently I was. Anyway, here's a problem as directly read from your Louis Leithold TC7 book on page 220. A cardboard box manufacturer wishes to make open boxes, meaning no top, from rectangular pieces of cardboard with dimensions 10 inches by 17 inches by cutting equal squares from the four corners and turning up the sides. We wish to find the length of the side of the cutout square so that the box has the largest possible volume. So what do we wish to find? The length of that cutout on the corners so that we maximize the volume of the box. So let's picture what's going on here by drawing a picture. Donde está? There it is. My straight edge. Forgot about my glasses too. Protect my eyes. So 10 by 17. Draw yourself in box. It's really just a rectangle. Okay, good enough. And here's the deal. We've got this piece of cardboard, and its dimensions are 10 inches in width by 17 inches in height or length. That is a fixed deal. And what's going on here is this box manufacturer has ordered a bunch of these 17 by 10 inches pieces of cardboard and wants to make boxes. Obviously, a flat piece of cardboard is not a great box. And so what he's going to do is he is going to cut squares out of the corners. Squares meaning they have the same width and height. And then he's going to turn up the resulting pieces to make a box. Okay, and the question is, and what we are after is, what is this length or height, which is the same for a square, of our square that we need to cut out in order to maximize the volume of the box? Okay, you can kind of picture that. If we do like a really small cutout, you're going to have a really big box that's very shallow. And the more you cut out, the taller that box gets, but the skinnier it gets. Okay, so kind of picturing the different dimensions of this box. And somewhere between the flat box and the like super skinny box is the maximum volume. Okay, and so we are going to use calculus to find it. But before we do that, we need to come up with an equation of the volume of our box that is dependent upon, that is a function of this cutout side. So let's see if we can do that. So let's maybe call the length of our sides of our squares, let's call those x's. Okay, and indeed all of these are going to be x, okay, because these are squares. So every potential side length here is x. And so if we recall that the volume of anything that is a prism, not just anything, but a prism, is its base, area of its base times its height, or for a rectangular prism, the base times the length times the height. So we need to figure out what is the dimensions of this box going to be in terms of x. Well, where do we want to do this? Yeah, let's do underneath. So volume of our prism is going to be equal to base times width times height. Is that what we call it? Yeah, sure, whatever. So the question is, what is base, width, and height? Well, it's going to, if we want it in terms of x, we need to think a little bit. Hopefully we can see that the height of our box, when we fold up these corners, is whatever x is. Okay, the height is going to be x. Oh, this should be length. I'm forgetting geometry. Let's call it length. Length times width. That's what I was looking for. Length, width, height. So then the length, which maybe we'll call this dimension that I've currently got labeled 17. But obviously when we cut out the corners, it's not going to be 17 anymore. It's It's going to be less than 17. And it's going to be exactly 2 x's less than 17, because of this 17 distance, when we cut out a square on each side, there's an x here and an x here that gets removed. It's going to be 17 inches minus whatever x ends up being. And in like manner, the width of our box with a maximum width of 10 also gets crushed by, or minimized by 2 x's. When we cut out these corners, an x comes out on this end and an x comes out on this end. And so the width here will be 10 minus twice the length of x. Okay. So now we're in a position to actually create a volume function as a function of our cutout. Okay. And so if we're kind of picturing, maybe it's kind of going to help to draw this real quick. If we've got a picture of what this box is going to look like. Okay, something like that, where this is our width of 10 minus 2x. Here's our length of 17 minus 2x. And here is our height of x. And it's an open box that you put stuff in, because that's what you do with boxes, you put stuff in. I'm picturing maybe like a Nordstrom's box or something, like the bottom of it, where you put the clothes in. Okay. So then our volume as a function of x, where x is that length of our cutout square, is going to be our length of 17 minus twice x times our width of 10 minus twice x times our height of x. Okay. Which, because we're going to be taking a derivative here, it'll probably be easier if this is in more of a standard polynomial form, because then that'll be a pretty easy derivative to take. I suppose we could do some product rule here, but let's just make this look more differentiable. And then before we do the derivative, we are going to have to ask a pretty important question that's going to be asked of every single question in this section, and that is, what is the domain of our function? Because to do our absolute extremum, we're going to have to figure out what the endpoints of some closed interval are, which is going to be our domain. Okay, so multiplying this out, we get like 170 minus 34x minus 20x, that's like 54x's plus 4x squared times x. So the volume with respect to x is going to be 4x cubed minus 54x squared plus 170x. Cool. Now here's the important part, or a important part. There's a lot of important parts here. What's our domain? And this is where the Mr. Smith talks about calculus format really falls short. Usually at this problem in this lecture, there's a heated discussion, maybe not heated, but spirited discussion about what can the domain be for this function. Keeping in mind that the domain is going to describe the potential values of our input. Okay, all the way back to algebra 1. What are the potential values of the length of a square cut out for this box? Okay? And like the lazy, easy answer is, 0 to 17. Because that's like the biggest length here. But does that actually make sense? Can we actually have squares that are 17 inches long? No. Okay. For this length, the most we could do is half of 17, so like 8.5. And that's way too big for 10. So 10 is going to be the limiting factor here. Oh, so it's 0 to 10. Well, no, because again, the side length of the square, there's got to be two of those. So the very biggest square that we could cut out from a length of 10 is 5. Now that's not going to be a very interesting box because it's basically just going to like fold up on itself. But 5 is the absolute biggest. And in a like manner, 0 is the absolute smallest. Okay. Again, there is room for discussion on whether or not 0 and 5 actually constitute boxes if you were to cut those for real. But for the purposes of our problem and the purposes of being able to apply the extreme value theorem, we are going to say that our domain is from 0 to 5 inclusive. Inclusive. Fully understanding that if we actually plug 0 and 5 into this function, you get no volume. Okay. The 0, 1 is easy to see, but if you want to just test me real quick, if you plug 5 in for x on the function that we just defined, you will also get 0. So those are kind of that's the worst box you can make. So somewhere between 0 and 0, we're going to get like a peak volume before it falls back down to 0. We're looking for that peak. We're looking for, okay, it's rising, it's rising, it's rising, the tangent line, flat lines, and then falls. That flat line is our maximum volume location, okay? So, and yeah, let's just do this. Let's just show you that that's what we're after, okay? So these are just fun all around problems. So we get 4x cubed minus 54x squared plus 170x for our window. We're going to go like, well, we know that the domain is like 0 to 5, so let's go, I don't know, 0 to 6. Give you a little room. And then since I've done this problem before, I know that we need to go from like 0 to, let's say, I don't know, 200. Let's see how that goes for us. Oh, beautiful. Oh, beautiful. Okay. So you think, oh, so this is like a quadratic function? No, we just said it's a cubic function. Okay. But the part that we care about is right here. Okay. And so we are looking for this right here. And if we're picturing our tangent line, okay, like positive, 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 getting less positive, getting less positive, let's get less positive, 0. And we want to know when is that 0, because then it, like the tangent line goes negative, 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 negative. You get the point. This is what we're after. This is what calculus lets us do, is find this horizontal tangent and say, oh, that's where it's maximum. Cool. So let's do that. Because now this is the hard part. Now we're just kind of doing some easy derivatives and plugging some numbers in. The setup is the key and the establishment of what our domain is. And I'm not going to pretend like this was just a walk in the park. It requires some creativity and critical thinking. But as calculus students, I have full faith in your ability to do both those things, be creative and think critically. Anyway, what we need now is the derivative. Okay. So derivative of v of x will allow us to find critical numbers. So v prime of x is equal to 12x squared minus 108x plus 172. So we want to know, when is this equal to 0? Remember, critical numbers mean that our derivative is 0 or non-existent. Well, a polynomial exists for all real numbers, so there is no D and E derivatives in this case. So our critical numbers are going to be specifically where this is equal to 0. So in other words, we want this equal to 0, 12x squared minus 108x plus 170. I think a 6, now maybe a 2 comes out of all these. Yeah, 2. This will be twice 6x squared minus 54x plus 85 equals 0. And then we're going to use this quadratic in our quadratic formula and figure out what x can be. So we all remember the quadratic formula. X is equal to negative b, that's 54, plus or minus the square root of b squared minus 4 times a times c. Yuck. Anyway, all over twice a. Cool. So x is going to be equal to 54 más o menos. I'm going to assume that you can pull out your calculator and do that part. And I'm going to just tell you that it comes out to 876. Magic. All divided by 12. Which means hello, come to the party. There are two options here. X is either approximately equal to 6.97 or x is approximately equal to 2.03. So now we're going to use the extreme value theorem to figure out what our options are and what is the maximum. So set up our XY table. I guess our X VX table. We know X is minimized. Sorry, the minimum value that we can plug in for X is 0. The maximum is 5. And then we've got 2.03. Oh, whoa. There's no place for 6.97 because it's not in our domain. It's not enclosed within 0 and 5. So we don't have to check that one. Cool. Not in domain. Cool, cool, cool. So our potential volumes for our absolute max or absolute extremum are 0 and 0 or 0 and 5, which means that this one better be our max volume because that would be a lame box if it was 0. And so then going back to our calculator, y1 is our function, so we can go y1 of, and we're going to go exact here since we can. It's going to be 54 minus the square root of 876. Nope. Diviso 12. Close parentheses. And we get 156.03, we'll call it. Cool. Cool, cool, cool. So our conclusion then, this is important to do with all these problems so that we can actually convince somebody that we actually know what this means. Conclusion. The largest possible volume of our box is 156.03 cubic inches. Okay, again, we had this discussion, or at least I said this, but there was no discussion because you guys weren't here, about the idea that the maximum value is the function value. 156.03 cubic inches is the maximum volume. It's not 2.03. 2.03 is where it happens. Okay? So the largest possible value, the absolute maximum of the box is 156.03 cubic inches. And then you can make note of the fact that it happened when those cutout squares are 2.03 inches. Okay. Obtained when the length of the cutout squares, cutout corners, maybe cutout corner squares, there we go, is 2.03 inches. And this is a chance for you to show off that you actually understand what just happened. Oh, we maximized the volume of the box. There's the maximum volume. And it happened when the length of those cutout square corners was 2.03 inches, okay? Unit's important here because it, again, illustrates that you understand what's happening. This one-dimensional length was when we obtained this three-dimensional volume's maximum value, okay? The more you can show that you know, the better chance you have of convincing me and then eventually convincing the AP reader that, oh yeah, this person knew what they were doing. They weren't just mashing buttons on their calculator and hoping that something good happened. Which is a time-honored tradition, and sometimes you just have to do that if you're not sure what to do. But hopefully we can all get to the end of a problem and just succinctly say, this is what we did, this is what we found, this is why. Cool, 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 cool. Onward and upward. So that was the cardboard freaking box. Not that bad. I don't know why I was so angry last year. Probably because the Dodgers were losing. And they're winning, so I'm in a good mood. Okay, ejemplo numero, I call it example 2. Did I change this? I might have changed this problem. I think I did change this problem. I made it more interesting. Yeah. Yeah, so the next problem is going to be similar to example 1, but I actually changed it so that we get a more interesting answer. I think, did I? Possibly? Sure. Yeah. So here's the sitch. We have got, what are we trying to do? Yeah, so we've got this situation where we've got this river that's wide, okay? And you've got a telephone company that is trying to lay some wire from 2 different points on the riverbed. And the rub here, the reason this is an interesting problem, is that for this telephone company, there is a certain cost associated with doing underwater wiring and a certain cost associated with doing above ground wiring. As you can imagine, the underwater stuff is more expensive. And so they want to find the sweet spot of finding how much of that distance to cover underwater and how much to do on the ground, okay? And so we're going to figure out, when does that happen? So this is a fun little problem. So example 1. I think the picture coming first here might help show what we're trying to do. Example 1. Underwater telephone wire. Okay. So let's draw this out. And again, this is not exactly the same dimensions as in the actual example one. So that'll give you a chance to do this again if you want with a new problem. I think what ended up happening in the book problem is that your maximum value, or your minimum cost rather, because that's what we're after here, occurred at one of the endpoints, which I wasn't super keen on. So we're gonna actually, I finagled the problem so that we actually have an answer that's in between our endpoints of our domain, which is kind of cool. So here's our sitch. We've got a river, and you've got some starting location over here called A, and we're trying to get to C. Okay, I think they're like, again, maybe they're antennas or something for a telephone company. Okay, so we're trying to get to C with some telephone wire. And then there's also a point B directly across from A. And the deal is, if we're on land, the wire is going to cost us $1.5 million per mile to lay. Some fancy 5G stuff, I don't know. Underwater, it's going to be 2 million a mile. So obviously there's a balance here between trying to minimize the amount of underwater and maybe maximize the amount on land, but maybe it's not just shortest distance online or underwater and longest and as much on land as possible. Okay, so what I kind of want to show is what we're trying to do here, because it can be a little tricky. We're going to say that the width of this river is 1 mile, and the distance from B to C is 3 miles. Okay. So before we even worry about like a function here, if we want to think of like the two obvious costs that we could do here, we could go straight across the river to B and then cut from B to C. So we do the 1 mile underwater for $2 million. And then we could do the 3 miles on land at a cost of 1.5 million per mile. So an additional 4.5 million. So that'll be a $6.5 million project. Okay, that's one option. Or we could go straight across from A to C, do it all underwater, which would be whatever the hypotenuse of a 1-3 right triangle is. So like square root of 10. So square root of 10 miles at $2 million a mile. $6.3. So that would actually be cheaper. Okay, so the question is though, is there, so again, the two options are straight across, so do like the two legs of that right triangle, or do the hypotenuse. And of those two options, actually the hypotenuse option is cheapest, just go straight across. What we're trying to figure out is if there is some intermediate point in between B or C, where we could just go part of the way underwater, which would do two things. It would minimize the distance underwater, at least some, and it would also cut the distance that we're going on land. So is there some intermediate, better solution here to minimize the cost of our project? Okay, fair question. And so again, we've got the two obvious cases. Is there an intermediate one? Well, how do we even write a function for that though? That's the tricky part. Okay. Well, we kind of got a clue with thinking through this length here. This length was the hypotenuse of some right triangle, okay? Well, the changing quantity here is this distance between B and P. Where we're putting P is changing our quantity. So X is some distance from B to P, which means if we wanted that, basically there's gonna be two things that go into the cost. This length and this length. On the one end, we went straight across and boom. On the other end, boom, okay? So this hypotenuse is going to be the square root of 1 plus x squared. That's just straight up Pythagoras. A squared plus b squared equals c squared. So c is equal to the square root of a squared plus b squared. If you're not seeing that, press pause and convince yourself that that's true. So our one length is going to be that. This is going to be the cost of our underwater. And then what's left to go from P to C is that 3 miles less X. And that will be the cost of our on land. Okay, are we buying that? Are we buying that? I hope so. So if we're going to turn this into a cost function, the cost with respect to the distance between B and P is going to be $2 million times this length here. This is the underwater distance, costs us $2 million. That's the square root of 1 plus x squared, plus $1.5 million times the leftover distance, 3 minus x. Okay. The domain here were those two options that we verbally talked through. You could have just a straight across shot, in which case x is 0. And we said that option, and we'll go back and show that again, but I think that option was 6.5 million. Or you could not do any underwater, meaning that x is 3, so minimizing the on-land distance. So x is measuring the distance that we're not doing on, that's maybe a good way to think about it. The distance we're not doing on land, okay, which goes from 0, meaning we're doing all of the distance on the land, to 3, meaning we're doing none of the distance on the land. Okay, so we've got our domain, we've got our function, we can do the extreme value theorem, which means take the derivative and see if we can find some critical points. So c prime of x, let's maybe rewrite our function with rational exponents. So what do we want to do? Yeah, that's what we want to do. So dx of 1 plus x squared 1/2 plus, let's call this, I don't know, 4.5 minus 1.5x, just distributing, and then differentiate. So this first guy is going to be a power rule with a chain rule. So we'll get, oh, did I lose a 2? Did I lose a 2? Yes, I lost a 2. Don't want to lose a 2. There's the 2. Okay. Drop down that 1/2, which cancels the 2, so that's probably why I lost the 2. And we get 1 plus x squared. Taking 1 away, we get negative 1/2. The chain rule inside here pulls out the derivative of 1 plus x squared, which is twice x. Derivative of 4.5 is 0. Derivative of negative 1.5x is negative 1.5. Okay. Which is equal to twice x over the square root of 1 plus x squared minus 1.5. Okay. So now, 2 questions. Is there anywhere that this derivative, c prime of x, does not exist? Is it possible to blow this thing up? And I think the answer is no, because even if we try to throw negative numbers in here, you're going to square it and add something to it. So this is always going to be positive in here. So I think we're chilling. We can put anything in here. So no DNEs, especially on our domain. 0 and 3, we're all safe. So no DNEs, which means we're specifically looking for when is it equal to 0. So c prime of x exists for all x on domain. So check, when is c prime of x equal to 0? In other words, we want twice x over the square root of 1 plus x squared minus 1.5 equals 0. Looks a little scary, but I don't know, we're calculus students. Let's figure it out. So we get twice x over the square root of 1 plus x squared is equal to 0.5. Multiply both sides by square root of 1 plus x squared, because I don't know what else to do. 2x is equal to 1.5 times the square root of 1 plus x squared. I'm thinking maybe we should like square both sides. Get rid of that square root. I don't know. Let's figure this out. This turns into 4x squared. Over here we get 1.5 squared, which is like 2.25? I'm going to cheat. Yeah, 2.25. And I'm going to do 2 things at once. This goes away, and I'm going to distribute. So 2.25 plus 2.25 x squared. Subtracting 2.25 x squared from both sides, we get like 1.75 x squared is equal to 2.25. And then dividing both sides by 1.75, we get x squared is equal to, I'm going to do this, I'm not going to simplify this because I'm not going to, 1.75. Taking the square root of both sides, square root, x is approximately equal to why am I using old pink? Let's use this guy. Second, square root 2.25 divided by 1.75. 1. We'll call it 1.13. All right. So here's the fun part, because we didn't look at the curve of this thing. It could be that this is a maximum or a minimum. We don't know. We're after the minimum because we're trying to minimize costs because we're business people. We want lesser costs. So we've got our critical number. We've got our endpoints of our domain, which we verbally talked through, but now we're going to do it for real. So let's set up our table now. We've got our x. We've got our cost with respect to x. And we're going to see which of these 3 numbers, 0, 3, or 1.13, minimizes our function because we want to pay less cost. C of x is our cost. Okay, so I verbally kind of walked you through what 0 was going to be, but we'll plug it into our function and see. So if 0 means we're going straight across, we're doing the 2 legs of that triangle. So according to our function that we wrote, that means twice the square root of 1 plus 0 squared plus 1.5 times 3 minus 0, which, as we said, 2 times the square root of 1 is 2, 1.5 times 3 is equal to 6.5. 6.5 millions. For 3, we get 2 times the square root of 1 plus 3 squared plus 1.5 times 3 minus 3. So this is the case where we're just going straight from A to C, doing nothing on land. It's all underwater. And that length, that hypotenuse, is the square root of 10. So twice the square root of 10 gives us a cost of, actually it's still on my calculator, it's called 6.32. So right now, the fully underwater option is the best. It's the best. So our task is to see if we plug in 1.3, do we get a number smaller than 6.32? And if we do, that's going to be our minimum cost. So we're going to do, pardon me, 2 times the square root of 1 plus 1.3 squared, sorry, I wrote it like that, plus 1.5 times 3 minus 1.13 equal to, we're just going to do this all at once in our calculator because we can. 2, that's what I want, 2 times square root of 1 plus 1.13 quantity squared. Yeah, we're good. Times 1.5 times 3 minus 1.13. Where did I screw up? Oh, that needs to be a minus, not a negative. And then press enter. Oh, look at that, 5.82. We found the minimum, 5.82. Oh, happy day. So this is our absolute minimum. Because we've checked the endpoints. This is a critical value. And because it's the smallest number, that is the cheapest way we can get it done, which means the absolute maximum would be 6.5. We can spend between 6.5 million for the most, or if we're smart, we can do 5.82 million. So our conclusion here. The cost of wiring is minimized when the wire is directed, let's say, to a point 1.13 miles horizontally from the starting point This was a little wordy because it's kind of a hard thing to describe. And that minimum cost is $5.82 million. Cool. Cool. Try something that I have not previously tried. Pause. I'm going to pause the recording and go do something real quick, and I'll be back. See if that works. All right. So hopefully that pause situation worked. So I'll find out afterwards if it didn't. It would be a bummer. So we've gone through 2 of these problems. We got 2 more. And then we'll call that a day. So moving on from example 1, we are going to jump into example 3, example 2. Example 2. No, example 3 I said. Example 3 is all about maximizing area. Of fenced in region. So, I think this is actually just straight out of the book, so let's see what the book has to say about this issue. A rectangular field is to be fenced off along the bank of a river where no fence is required along the bank. Okay, makes sense. If the material for the fence costs $12 per running foot for the two ends and $18 per running foot for the side parallel to the river, find the dimensions of the fence. Find the dimensions of the field of the largest possible area that can be enclosed with $5,400 worth of fencing. Support the answer graphically. Okay, so here's the deal. Again, sometimes a picture helps inform what's actually going on, what we need to worry about. We've got a river. We're building a fence. It's a three-sided fence. You don't need to fence in the river. And if we're going to call the one distance x and the second distance y, so you got the perpendicular and you got the parallel. And for whatever reason, it's different cost depending on which way the fence is going. Don't know why that would be, but it just is. Okay, so it's $12 for each x foot and $18, so each of the perpendicular feet, and $18 for each y foot. And we want to maximize volume with $5,400 to spend. Okay. So, a couple different things going on here. We've got a volume, not volume, an area that's pretty easy to figure out, x times y. Okay. But then the thing that we actually care about is the cost based upon x and y. So let's maybe write that cost situation first. Okay. The cost is going to be determined by 12 feet per x foot, but really there's two of those, so plus another 12 foot for each of those x feet, plus $18 for each y foot, and this is going to equal $5,400. And we want to know what values of x and y are going to maximize the area, but still hold to this equation. So basically, we've got this equation, but what we're trying to do is figure out for area of our thing as a function of x, let's say. Now let's forget that for a second. Area is equal to x times y. Well, we don't really like functions of two variables, and there is two variables here. So what we can do is write area as only a function of either x or y. It doesn't really matter. We're kind of used to writing it in terms of x. So the area in terms of x is going to be x times y, okay, so we need to write y in terms of x. And that's where this cost situation is going to help us, because we can rearrange this and solve for y. So need y in terms of x. I have our side hustle over here, is we're going to say that 18 y's are equal to 5,400 minus 24 x's. And then dividing everything by 18. Believe it or not, 18, I guess that makes sense, goes into 5,400 300 times. And then 24 divided by 18. There's 6's in both of those, 4/3, yeah, 4/3, 4/3 x. So this is the relationship between y and x. So now we can say, oh, okay, yeah. The area that we're trying to maximize is not x times y, but x times what we just figured out y is, 300 minus 4/3 x. Cool. Cool, cool, cool. Domain. Domain's a little tricky. Domain is a little tricky. So let's think about the domain. Off to the side. So probably the smallest we could do for x is 0. You just have one super skinny long fence where we're just using all of the y feet. Okay, you can picture that. What's the biggest that x could be? That's maybe not quite as intuitive, but basically the biggest that x can be is when y is 0. So super linear, skinny long fence the other way, which again is not going to have any volume, which is kind of silly, but we can still picture it. So when y is equal to 0, so this is, yeah, I'll just do it here. When y is equal to 0, that's going to mean that 4/3 x is equal to 300. Multiplying both sides by 3/4, we get that the biggest that x can be is 225. Cool. Sometimes the domain part is the hardest, or just the thing that requires you to actually slow down and think. 0 to 225. Cool, cool, cool. Well, now we can go searching out, because this is, slow down. We're pretty well assured, and we'll plug it in at the end and see, but that if you plug in 0 or 225 to our area, you get no area. And we're trying to maximize our area. So our endpoints for this absolute value, absolute extremum problem, are probably not the endpoints. Okay, the maximum is going to occur somewhere in between, when x is somewhere in between 0 and 225. So we now go hunt out where that happens with our derivative. So the derivative of our area is going to be, I'll just write this out. Okay, it's going to be dx with respect to, derivative with respect to x of 300x minus 4/3 x squared, which is like 300 minus 8/3 x. And so we want, when this is equal to 0, to find our critical numbers. Clearly this is going to exist everywhere, so there's no DNE critical numbers here. So we need 300 minus 8/3 x to be 0. So we need 8/3 x to be 300, which is like, I don't know, man. What does it work out to be? 900 over 8? Sure. Which my notes from last year say is 112.5. And this is where it's important to stop, take a deep breath, figure out, okay, what does 112.5 mean? Oh, I know. 112.5 is the length of that perpendicular section of our fence that is going to maximize the area. It's going to maximize the area. So this is not the area. We still need to figure out what that is. But this is the input that will give us that maximum area. So going to our table, we got x's and a sub x's. Only got 3 here. Got our endpoints of 0 and 225. And now this critical number of 112.5. So for the 0 value, area is going to be 0 times 300 minus 4/3 times 0, clearly just 0. For 225, we're going to have 225 times 300 minus 4/3 times 225. 4/3 times 225 is 300. 300 minus 300 is like 0. And when I say like 0, I mean exactly 0. Okay, so these are both dead ends. These will not maximize our volume. So whatever this ends up being is going to be our maximum. Sorry, I keep saying volume, I mean area. We're talking about two-dimensional space. So we're going to get 112. I guess we'd use this one. That's probably smarter. Oh, well. Yeah, 300 times 112.5 minus 4/3 times 112.5 squared. $300 times 112.5 minus 4/3. Just make sure that we're double careful. 4/3 times 112.5 quantity squared. No, 16,875. And then prove it to me that you actually know what this means. Sure, I know what this means, Mr. Smith. I've been paying attention. The largest possible area that can be enclosed for $5,400 is 16,875 square feet. That is the absolute maximum. Remember, this is the maximum, not this. This is the maximum. It occurs when, or obtained when, the fence section perpendicular, so X was the fence section perpendicular to the fence, or to the river, is 112 feet. Cool. Cool. Okay, uno más y después vamos a estar terminando. No sé si este es correcto, pero no hablo español muy bien. Hablo español del gringo. Y pienso que si quiero decir we are finished, or we will be finished, voy a decir que vamos a estar terminado. Terminado? I don't know. I took 4 years of Spanish, but that was like 15 years ago. I don't remember anything. Sorry, guys. All right, example 4. Do one more and then we'll be done. So this is 9:28. The bell rings at 9:52, and I intend to be walking at 9:52. Mrs. Barahona. I am recording a lecture for my Calc kids. No, kids, don't be offended. We're okay. Do you need help? Okay. All right. That was my neighbor, Mrs. Barahona. She's a good lady. I call her my work wife because, like my actual wife, she keeps me appraised of the things that are important in my life, like what day of the week is it, and what's the schedule today, and are there important emails that I need? So I'm basically helpless. And during the not at work hours, Mrs. Smith makes sure that I'm not falling down on my face. And while I'm at work, Ms. Barahona next door does the same. So pretty nice, you know? You gotta know your limitations. I've got a lot of them. So it's nice to have people like Mrs. Barahona and Mrs. Smith in my life. Keep me from falling on my face. All right, example 6. Example 6. This one's a fun one. It's got some similar triangles in it. It's got like cylinders inside of cones. It's like good. It's fun. It's what it is. So let's do it. It's the greatest volume of a cylinder that can be inscribed inside a cone with radius 5 centimeters and a height of 12 centimeters. Oh, picture. So, well, first the question. Greatest volume of a cylinder inscribed and scribbled. There's not an L in that word. Don't write the L. It's just inscribed. Inscribed inside a cone. What? This problem is bonkers. Inside a cone whose radius is 5 centimeters and whose height is 12 centimeters. So picture all day. We gotta visualize this. It's a cool problem. It's bonkers. It's a little nuts, but we can do it because we're dolphins. Fins up. We got this cone. We're gonna assume it's like a regular right cone. So cone, circular base. Cool. Whatever. We've seen cones. Not impressed. This one in particular has a height of 12 centimeters and a radius of 5 centimeters. So here's where it gets a little bit bonkers. We're being told that there can be a cylinder inside of the cone. And we want to maximize the volume of that cylinder. Okay, we know the volume of the cone. We can do 1/3 pi r squared times height, find the volume of the cone. But what we want to know is like, hey, if we just threw in some cylinder here, inside, inscribed, what? Are you seeing how nuts this problem is? It's a little bit nuts. Okay. What's the maximum volume of that cylinder? Well, let's feel out kind of like the domain here. So the deciding factor of this problem is going to be the radius of the cylinder. Okay, and so the radius, if we let it be 5, you're gonna have a really thin, short cylinder because as soon as it tries to get taller, it gets blocked. Okay, it can't go that high. Okay, so it's just flat. Or you could have a radius that's very small, dare I say 0. That's going to be like just this non-existent rod up the middle. So thinking about radius, sometimes you go out of order here and just think, okay, what are the dimensions of what are the possible dimensions? Well, it can be the really long skinny guy, the wide skinny guy, radius of 5, or if you had no radius, it would be like that. So somewhere in between a radius of 0 and 5 is a sweet spot where we have the most volume for that cylinder. Okay. So let's maybe label some more stuff. So if we're going to do the radius of our cylinder be little r, and then we're going to have a height of our cylinder, because those are sort of the deciding factors for the volume of any cylinder. Because for a volume of a cylinder, we get pi r squared for the area of the base times the height. Okay. But not that okay, because now we've got two unknown things, because the height in large regard is going to depend upon the radius. How tall we can go is dependent upon how big we decide the radius is going to be. Okay, and we saw that when we considered the extreme conditions. When the radius was 5, the height had to be 0, because you're just at the edge and there's nowhere to go up and still be inscribed in that cone. And same thing, when it's 0, the height went all the way up, because it could go all the way up, but then it eventually stopped at the top. And so we need to see if we can figure out, can we define h in terms of r? Because we know that h is dependent upon r. So that's probably the way we want to go. So the way that we're going to do this is kind of tricky, but we've seen it, I think, with related rates, and it keeps cropping its head up. So we need to keep our eyes open for this scenario, that when we have things going on inside of cones, there's usually some similar triangles that we can tease out of it. So here's what I'm talking about. If we were to maybe use a green pen here, because I don't know, why not, draw in that total height, check it, check it, check it. And I'm going to redraw this, but this right triangle, which contains this right triangle, ooh, those are similar triangles. Let's see if we can make some magic with that. So I'm going to just redraw this green triangle outside. So bada boom, bada bing, bada bam. Okay. So we know the big triangle, because we just pulled it straight out of our cone, has a base of 5 and a height of 12. Okay. What happened to the cylinder triangle? Oh, okay, yeah, the radius. So this line was the radius that was r of our cylinder. So if we're kind of picturing, this is like half of our cylinder. Okay. And then this guy right here is the height. The height. Okay, so I'm just kind of transplanting that. Now we've got two similar right triangles. And we know the wonderful thing about similarity, the reason that trigonometry works, is that they're proportional. The sides between similar triangles are proportional. So the ratio between sides is always the same, which is why the unit circle works, and it's the best thing ever. But for this, we're going to say, I don't know, we're going after h. So how do we want to do this? I guess we could go, let's go small part to big part, small part to big part. Oh, which means we also need to talk about this distance here. Well, we'll see that need in a second. So setting up a ratio, or a proportion rather, that involves two ratios. We're going to have the ratio of r to 5, so those corresponding sides, is going to be the same as the ratio of this small part to this big part. We know the big part is 12. And what we now see we need to define is this part, but because we went through the trouble of saying that this is h, hopefully we can see that this leftover part is the difference between 12 and h. 12 minus h. So that side of our small triangle is 12 minus h. And now we are going to solve this for h so that we can plug it into our volume function and have the volume just be a function of our radius. Okay. So doing some rearranging, you get like 12 r's are equal to 60 minus 5 h's. We have like 5 h's are equal to 60 minus 12 r's. And so we get that h is equal to like 12 minus 12/5 r. Sure, why not? Is that a thing that works? Yeah, we'll say that works. Cool. Now we got h in terms of r, and we are happy campers because now this volume of our cylinder can be our volume as a function of our radius only. And we can define this as pi r squared times 12 minus 12/5 r. So much better. So much better. In fact, let's distribute this, and we get like 12 pi r squared minus 12/5 pi r cubed. And there's our volume function. And we want to know when it has its max value, which means finding critical numbers, which means finding the derivative. So v prime of r is just straight up power rule. We'll drop down that 2, get 24s times pi r. Power rule here gives us 36/5 pi r squared. And we're going to figure out when is this equal to 0. This is going to be gross, but it's okay. 24 pi r minus 36/5 pi r squared equal to 0. We'll pull out an r from both sides, from both things, and get 24 pi minus 36/5 pi r equal to 0. So one of our options is when the radius is 0, but we're already pretty sure that's not going to work too well because that was one of our domain extremes that we considered. So really we're going to look at when is this thing equal to 0 in here. In other words, when is 36/5 pi r equal to 24 pi. I don't know why I let these pi's survive for so long. Let's get rid of those. Later, dogs. Later, dogs. So now to get r, we're going to multiply both sides times 5 over 36. Cool. There's 6's all over the place. So 6 into 24 is like, oh, there's 12. Let's do 12. Yeah. 12 into 24 is 2. 12 into 36 is 3. So our answer here, our radius, is 10 thoids. Okay. Critical number. 10 thirds. 2 and 1/3. Oh, we forgot to write down the domain. We're okay. Recall. Remember. Domain for R is 0, the really tall skinny cylinder, to 5, the really flat wide cylinder. And so when we're doing the extreme value theorem, we're going to set up a chart. With those endpoints, 0 and 5, and with this guy, our critical number, 10 thirds. And I guess we should say that R can also equal 0 here, but from our domain, we see, okay, that's already kind of covered. So the volume here, when it's 0, when the radius is 0 is 0, when the radius is 5, it's also 0. So we need to figure out what is the volume when our radius is 10 thoids. Where are we going to plug this into? I don't know, bro. Not my party. I guess it is kind of my party. I guess we'll do that one. I don't know. This is gross. Yeah. So we'll do pi times 10 thirds squared. Is that how we're going to do it? No, let's do 12 pi times 10 thirds, yeah. 12 pi r squared minus 12 fifths pi times 10 thirds cubed. Yeesh. So this is going to turn into 100 ninths times 12. So 1200 ninths pi minus, it's going to be 1027ths. Ew. But then the 5 is going to cancel with the 1,200 times. The 12 and the one of those 3's. Yeah, we're okay. So that's going to give us 200. Yeah, 200. I just need to do this. No, we got this. Let's mental math this. Okay, so we're going to get 1,027ths, or multiplying times 12. I guess we're not mental mathing. I'm actually writing this out. Times 12 fifths. So the 5 gives us a 200. The 3 gives us a 9 and a 4. 4 times, that's 800. Over 9 pi. Woo, we did it. And then we got the same denominator. And we get 400 ninths pi cubic centimeters. Because again, let's not lose the forest for the trees. What did we just find? Conclusion, tell me. We discovered that the maximum volume of the inscribed cylinder is 400 ninths pi cubic centimeters obtained when, because again, that is the maximum value. This is the maximum value. This is when it happens. Obtained when the radius of the cylinder is 10 thirds centimeters. Woo! That was a marathon. We did it. We've tackled 3.2 applications of the absolute. Ew, this thing is falling apart. Well loved. Okay. So that should be enough to make you dangerous. I'm going to press stop record, not just pause record. And we are going to call that victory. Stop recording.